Hello and welcome. In today's video, we are going to be going over more on U-sub. So, my entire plan for the next few videos is going to be go over U-sub again, then do integration by long division, then do trigonometric integrals, then do probably integration or trig sub, to put it simply, and then finally do partial fractions, and then do improper integrals, and then convergence tests after that. Well, to start out with the entire set of next videos, we have U-substitution, which is by far, in my personal opinion, one of the most important methods of substitution. So, U-substitution allows us to undo the chain rule derivative. So, to get started, we have this integral of x e to the negative x squared. Well, we have to find a function where we can also find the derivative of that function. So we'll say in this case, since we have a negative 2x squared, that's similar enough to x, or to the derivative, which is going to be negative 2x, for us to maybe use u sub. So in this case, we'll say u sub is going to be negative x squared. We then have to find the differential du by taking the derivative. So we get negative 2x. And then we multiply the du, or the dx from the du dx to the other side. We then have to solve for this dx in the integral, or in the expression. So we get du divided by negative 2x. And this is what we can plug into our integral. So we now have the integral of x e to the negative, and we'll call this now u rather than x squared. And we have du divided by negative 2x. In this case, the x's will cancel, leaving us with just the 1 over negative 2. So this is really just the same thing as the integral, or negative 1/2 times by the integral of e to the u du. Well, the integral of e to the u is just e to the u. So we get e to the u plus c. But we can't forget, we have to plug in our original. So we get negative 1/2 e to the negative x squared plus c. And that is our solution to the integral. For this next expression, I think it's a wise starting place is to maybe do sine, because sine's derivative is cosine. So if we say u is equal to sine of x, then our du must be equal to cosine of x dx. Solving for the differential dx, we get du is equal to 1 over cosine of x. We can now sub in for our u and our dx. Or sorry, our u and our du. So we will get u squared, since we have u is equal to sine, times by cosine of x, times by 1 over cosine of x, times by the differential du. Well, cosine of x and cosine of x will cancel, leaving us the integral of u squared with respect to u. This is just a power rule integral. So we will get u cubed divided by 3 plus c. But now we have to sub back in for our u. So we get sine of cubed of x divided by 3 plus the constant of integration c. For this next integral, I think a very good place to start with most integrals is setting u equal to the denominator. So we'll say u is equal to e to the z plus z. So then our differential du must be equal to e to the z plus 1 times by dz. Now we need to solve for this differential dz. So in this case, we'll get du divided by e to the z plus 1. So now we can sub this into an integral. We have e to the z plus 1 in the numerator. In the denominator, we just have u times by du divided by e to the z plus 1. Well, the denominator and the numerator will cancel, leaving us with the integral of du divided by u. This integral is just the natural log of the absolute value of u plus c. Well, if this is the natural log of the absolute value of u, and u is e to the z plus, or e to the power of z plus z, we get an expression of the natural log of e to the z plus z plus c. For this next integral, you might think, hey, maybe we should use u-sub. But let's try it. Let's see what happens when we do u-sub for this integral. Well, we have u is equal to 1 plus x squared. All right, that's not a problem. Well, du is now going to be 2x dx. So now we have to solve for the differential dx. So we get dx is now equal to du divided by 2x. We sub that into our integral, 1 plus x divided by 1 plus x squared, which is actually now just u, times by the differential dx, which is really du divided by 2x. And what's going to happen is we actually won't get this x to cancel. We would get a 1 divided by 2x plus 1/2 divided by u. We cannot solve this integral because it has more than one variable. So rather than doing this and making all this mess that doesn't lead to a solution, we're going to actually break this integral down using some integral properties. So we will say that this is the same thing as the integral of 1 divided by 1 plus x squared dx plus the integral of x divided by 1 plus x squared dx. This left integral should be an antiderivative, you know, from memory. It's actually just going to be arctangent of x. However, this left side needs a bit more work. It's going to start out, let's say u is actually equal to the denominator like we did earlier. So we get u is equal to 1 plus x squared. So our du, or the derivative of u, is really just going to be 2x dx. We have to now solve for the differential dx, so we get du divided by 2x. Now we're going to sub this into our integral, so we get x divided by u times by du divided by 2x. The x's will cancel, leaving just a remainder of 1/2. So we now have arctangent of x plus 1/2 the integral of du divided by u. Well, now I think we've gotten experienced enough to know exactly what this integral is, so we get the natural log of the absolute value of u plus c. Well, we know what u is equal to. U is just 1 plus x squared, so we can plug in 1 plus x squared into the natural logarithm. So we'll get this expression, arctangent of x plus 1/2 the natural log of 1 plus x squared plus c for our answer to the integral. Alright, for this next integral, I think this one's a small bit more challenging, as if you set u equal to the denominator, you would see that our du is going to be 4x cubed. However, if we were to sub this in, that would not get all the x's to cancel. So rather than selecting that to be our du, let's try u is equal to x squared. So even though we're not accounting for all the denominator, we're still accounting for the x, the x to the fourth. So we get du is actually going to be 2x. So then 2x dx. So then dx is equal to du divided by 2x. So we now get the integral of x divided by 1 plus u squared times by the differential dx, which is really du divided by 2x. The x's will cancel each other. So we are now really just left with is the integral of 1 half the integral of 1 plus u squared du, which is the same thing as 1 half tangent inverse of u. Tangent inverse of u is equal to 1 half tangent inverse of x squared. And always remember the constant of integration c. So this next integral, in my opinion, is a small bit more complicated. So I think where I would like to start is maybe setting u equal to the natural log of x. So we'll say u is just going to be equal to the natural log of x. So then our du is just 1 over x dx. And solving for our differential dx, we just get dx is equal to x times by du. We can now sub in u to our expression here, so we get secant of u squared times by tangent of u squared. However, we now also have 2 times by u. All of this is over x times by x du. This x and this x will cancel, so now we have everything in terms of u. But what is the secant of u squared? The answer is, I don't know. We don't have an expression for that, so we're going to try u sub again. So this time we're going to name another new variable. We'll call it z. Z is going to be the same thing as u squared. So dz is going to be the same thing as 2u du. Now we have to solve for the differential du, so we get dz divided by 2u. Alright, well, we can plug this into our expression, so we get secant of z times by tangent of z times by 2u times by dz divided by 2u. And would you look at that? The 2u and the 2u will cancel, leaving us with just the integral of secant of z tangent of z. Dz. Well, this expression here is the same thing as secant of z plus c. Well, secant of z is the same thing as secant of u squared plus c. U squared is the same thing as the natural log. So we get secant squared, or sorry, not secant squared, secant of natural log squared of x for our answer to this antiderivative, plus c. Alright. And please note that we don't have to keep the absolute value around this natural logarithm. And the reason for that is our u was the natural log of x, not natural log of absolute value of x. Alright, this next integral I think is a small bit trickier. So what is the integral of tangent, you might ask? Well, what do you take the derivative to get tangent? A stumper that one is, because there's not really a function you take the derivative of to get tangent. At least not commonly known. So what we're going to do is we're going to try and derive one. So we're going to say that this is actually going to be the same thing as sine of x divided by cosine of x dx. We're going to just try setting u equal to the denominator. We're going to say use cosine of x. Well, then our du must be equal to negative sine of x times by the differential dx. We now have to solve for the differential dx. So we get dx is equal to du divided by, or let's say negative du divided by sine of x. We're now going to sub this into our integral, so we get the integral of sine of x divided by cosine of x times by negative du divided by sine of x. Well, the sine of x and the sine of x will cancel. Cosine of x is actually u. I forgot to mark that down. And now what we're left with is the integral, and we'll bring this negative out front, of 1 over u du. Well, this is the same thing as the natural log of absolute value of u, negative natural log of absolute value of u, plus c, which, since u is equal to cosine of x, we get negative natural log of cosine of x plus c. And that is our answer. Alright, so for this last integral, it requires a small bit more work and a small bit more knowledge. So we're going to start by setting u to whatever is equal in the inside the radical. That's normally a good place to start. So we'll say u is equal to x minus 1. Well, what about this x right here? Would this get rid of that x? And the answer is no. So what we're going to do instead is we're going to solve for this x specifically in terms of u. So we'll get x is actually equal to u plus 1. We now just need to solve for the differential du using our original. So we get du is just going to be equal to dx. Pretty simple. So we're now going to sub everything in. We know u plus 1 is equal to x. So we'll say u plus 1 is we just stick it in place of x. Times by the square root of, well, x minus 1 is equal to u. So that's just the square root of u. And we're going to be integrating this because dx and du are equivalent with respect to du. We are now going to use our properties of exponents to make this into the integral of u to the power of 3/2 plus u to the power of 1/2 du. Now all we have to do is integrate these. So we raise the power by 1, so we get u to the power of 5/2, and then multiply by the reciprocal, which in this case is 2/5. Once again, we do the same. We raise the power by 1, so we get 3/2, times by the reciprocal, which is 2/3, plus c. But now you can't forget to sub in for u. So we get 2/5 of x minus 1 to the power of 5/2 plus 2/3 x minus 1 to the power of 3/2. And always remember the constant of integration c. Well, that's all I have for you today. I hope this video has kind of given you a bit more practice with U-substitution. And I hope you've found this video informative, and if you did, please make sure to like it. Helps me out and helps me know if you're liking my content or finding it informative.